My name is Kevin Basham, and this is CECS 447 Microcontrollers 3, Fall 2020, Lab 2, ADC, Measurement Data Acquisition. Brief description of the lab requires the student to create an embedded system which receives an input from a measurement actuator in this lab using the slide potentiometer here. Using an ADC to convert the analog signal to a digital signal, converts the digital data to a fixed point number, and outputs the converted measurement to a computer screen using ASCII characters. Briefly going over my code here. Let's see. Go ahead and open up all the main files here. Missing one. Which one is it? Okay, so this is the ADC C file. This file contains the analog digital converter initializer code. This code essentially sets up the volatile memory used to store the delay and the clock, inputs, outputs, the delay time, configuring for 125K sequencer, disabling the sequencer, setting up the trigger, setting up the channel, and then enabling it. And then this section of the code has a busy wait analog to digital conversion. This one here, I made sure to have a non-negative value, and what this does is it waits for the conversion, reads that result, sets an acknowledgement, and then returns the result from the ADC input. The Nokia C file was borrowed from Jonathan Vilvano, which was accompanied with the textbook. I found a resource here at this website which contained the majority of the code here seen. It was provided with the lab as a resource. Let's see. Measurement of distance C file is also provided with lab 14, which is the starter files that I started with when designing this lab. So there may be some overlap with my code and another lab called lab 14. General descriptions of what is labeled in here. Some generic strings also provided in the lab. Some unsigned longs to store values. Let's see. Alright, so this is the UART initializer. Use the UART to basically store the words that I'm going to contain my values. So it would send those signals back and forth between the microcontroller and analog digital converter. Let's see. So what this does is this basically initializes the UART. It activates port C for the UART, and then I had to do a little bit of calculation to figure out the total values used. Not sure how much detail you want. I could probably spend hours explaining each line, so I'll just go with a brief overview. This is the UART out char, UART out string. Both of those are provided and modified from the starter files provided in 346, I believe they came from. Not sure. That we've just been collecting files, and we're told we can reuse them. So that's what I'm doing. The UART convert distance, also borrowed. This code here is the card borrowed from previous class. Unfortunately, it still doesn't work exactly what I want it to do. I'm planning to mess with it some more as the semester goes on, but right now it's properly displaying a value, which is good enough for me. And then I have the conversion here. This was my regression formula. Funnily enough, I didn't really need to have a complicated one. 1.4 seemed to be pretty sufficient when I threw it into Excel. I tried a couple of values here on the side. The last one I tried was 218, but it works pretty well. Systic init, pretty standard. Set up systic during setup. Set the reload value for the 40 hertz frequency, which I believe was 199,999. Clear the current value, because setting any value there clears that. Then set priority 0, enable the clock. Setting up the systic handler to trigger every 25 milliseconds, collect a sample, convert to analog digital signal here. And then here, the main void, volatile, unsigned, long delay. My classmate Ian here made sure that this and some other values, when it wasn't working and I was going through the debugging stage, were volatile in order to, I'm not sure exactly why I haven't figured that out exactly, but for some reason changing to volatile works. And then we have the Texas init. And this is just my main function. So this is initializing Texas function for the Texas O files, which is included with the Volvano supplementary code. And then this was again EDC initializer that's setting up all the, these are just the function calls for all the things that I've already talked about. Systic init. This I ended up using 200,000 or 2 million instead of 199 because there's a off by one, but there will be 199 in here in certain places. And then enable the interrupts. Probably need to remove this code. It's just more dead code that I've been pulling in and out and using for tests. And then the main while loop, the super loop here, flag set to 0 because we haven't found anything, so this resets it. And then when the interrupt triggers, we get a flag. And then when that triggers, we convert the distance given the distance, setting the cursor to 0, which gives us our starting location on the LCD. And then we output the string provided from the system. And then I have this here, borrowed this from another one of the labs. Was doing some testing using the UART before I got my LCD display. Was actually able to display some of the information using the debugger on the I guess there's like a LCD thing that you can set up and you can test some of the values, so that was pretty handy. And then going over here to look at the current setup, don't mind the dots, I think that's from the loop code, still a buggy, but basically as we turn the dial, the measure of distance relative, I'm turning slowly here, relative to the distance will increase all the way to a max value if we turn it all the way up to the max value. And then if you wanted to turn it back, you could have it go all the way back. And that's the demo for lab 2.